Alright, this is our first one we're going to be doing with the homework. Since we've already gotten these two pieces of homework, I'm going to combine Getting Ready 1.1 and Getting Ready 1.2 on the same video. So, a little review here. Now, just so you guys know, I don't have a stylus yet, so I'm using my fingers here to write, which means they may get a little difficult at some points to do. Sorry about that, if that's the case. So, let's get going. So, let's take a look at a few of these solving equations. We're trying to get the variable by themselves. And remember, the point here is that we combine variables and then get the variable alone. So, if I'm looking at problem number 4, first thing I want to do is subtract 5x from both sides. By doing that, I eliminate, because 5x minus 5x is 0, and I'm left with negative 7 on that side. Because of this equal sign, remember, we have to always do things to both sides. So 7x minus 5x would give us 2x minus 17. Then I want to combine the numbers together, so I'm going to do the opposite, add 17. That eliminates that side, leaving me with 2x equals. Then I do, let's make that equal sign a little better. That negative 7 plus 17, when you add a negative and a positive, it's like you're subtracting, so it's a positive 10, because 17 is bigger. Separate the 2 and the x. 2x means times, so I'm going to divide by 2 on both sides. That'll get me x equals 5. So we basically do the same thing on the other side, on the other ones. Okay, so number 5. I'm going to add the 2x to get rid of the 2x on this side. But because of that equal sign, I have to add 2x on this side. And I only add x's in regular numbers together. So 3 plus 2 gives me 5x, plus 9 equals 44. Then I want to subtract 9 from both sides. Cancel those out. We get 5x equals 35. Divide by 5, and x equals 7. Now, you may do these slightly different. As long as you're doing the same thing to both sides and only combining x's or regular numbers, it'll work. Now, 6 looks a little different because this x right here doesn't have a number. So, how do we deal with that? Well, when x doesn't have a number, we can always put a 1 by it. Okay? That 1 is a ninja. It can appear and disappear with the x at will. So instead of just x plus 2 on the right side, we have 1x plus 2. So we're going to subtract our ninja x from the 3x. Those cancel. 3 minus 1 gives us 2x, plus 6 equals 2. Subtract 6 from both sides. 2 minus 6 will give us a negative 4. So 2x equals negative 4. Divide by 2. And x equals negative 2. So those hopefully were the easier problems you guys were able to deal with. Now on to one that gave a lot of people trouble. Okay, so if we're looking at this, we've got this pattern going on. And we're trying to figure out this pattern. Okay, the main thing you should hopefully notice is that from step 1, so that's what it looks like at first, to step 2, well, what did we do? Well, we basically added one block on each side except the bottom. Okay, and if you look over at step 3, we added one more box to that. Okay, so that's kind of what we're working with. So I could continue this and draw step 4. And how many boxes would we have? Well, and my boxes I know don't look the best, but you're going to have to deal with it. Okay, so now I've got 3 boxes on either side and 3 boxes on top. And that would be for step 4. So, number 7 says each square represents one tile. How many total tiles are in step 5, step 6? Well, let's count. Okay, in step 1 we have 1 tile. In step 2 we have 4. In step 3 we have 7. Hopefully you kind of are noticing a pattern here. How many blocks are we adding? How many square are we adding each time? We're only adding 1 on each side. Since we're doing it on 3 sides, we're adding 3 each time. Because 1 plus 3 equals 4. 4 plus 3 equals 7. 7 plus 3 equals 10 for number 4. So step 5, we'd add 3 more to that, and we'd get 13. For step 6, add 3 more to that, we get 16. Now, number 8 kind of extends this question. What might you do to determine the number of tiles in step 25? Well, we could just keep counting by threes, couldn't we? Step 7 would be 19. Step 8 would be 22. Step 9 would be 25. Step 10 would be 28. Then 31 for step 11. Step 12 would be 34. And you could keep doing this. Is this one tough to do? Yeah, that's going to make it a lot longer. So you want to try to figure out, is there a way that we can come up with a rule to help us with that? And that's kind of what number 9 is asking. What kind of rule can you come up with to figure this out? That's essentially what they're trying to help you do. It's a shortcut. Okay? You want to try to come up with a shortcut. And the best way to come up with a shortcut is you've got to somehow connect the step number with the total number. Because step 25 is what we have. We want to know how many tiles that gives us. So the trick is to try to connect the two and see if we come up with some sort of pattern. Okay? And that's pretty difficult. That's a very difficult thing to do, is to try to connect the steps with the total numbers. So for number 9, I'm not going to answer that. I want you guys to think about it. And we will see some answers in number 11 and 12. So number 10 wants you to try to figure out a different rule that you can use, because there's often more than one way that we can do these. Okay? One way we could write the rule for number 9, a very simplified way, would if we said, the previous number of tiles plus 3 is going to equal our current number of tiles. Is that a rule? Yeah, that's a rule. Is it a great rule? Not really, because it's basically like us just counting, like we were doing here, right? Where we just keep counting and 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 counting. Have we made it to step 25 yet? Let's see. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. That's how far we need to go. Can we do it that way? Yeah. We come up with 73. Okay, is that the best way to do it? Not really, but that does give us an answer for number 8. So this rule, does it work? Yes. Is it the best? Not really. Okay, so try to think of some different rule that you can to do that. And number 11 and 12 I think gave us some really good rules. And so we want to try to figure out how are they connected. That's what you want to try to figure out. How are they connected? Now I'm going to erase this ink, so you may need to pause it if you're still writing any of this down, so that I can give myself a little bit more room. Okay, so we've got Andrew, number 11. He comes up with this following equation. Okay, S I'm assuming means total number of tiles or squares, and N would be the step number. So let's write that down. N equals step number. Typically N does mean that in these type of equations, and S would probably be tiles, the number of tiles according to that step. It's pretty critical that you understand that. So where can we see these numbers? That's the question we're looking at. Okay, and if we look at this equation, basically what he's saying is if we take the step number, say step number 3, we subtract it from 1, then times it by 3 and add 1, that's going to get us our total number. Let's check it. Okay, we had what? 1, 4, and 7. Okay, let's try it. So 3 minus 1 would give us 2. 2 times 3 is going to give us 6. 6 plus 1 would give us 7. So it works. Okay, what about for number 20, for 25? What did we say that was? 73? So if we go 25 minus 1, that gives us 24. 24 times 3 gives us 72 plus 1 gives us 73. Okay, so it seems to work pretty well. So I'm going to erase this out of the way. So when we're thinking about that, where can we see it in the pattern? Okay, where can we find out this stuff in the pattern? Well, if we think about it, okay, the 3, notice that we were adding 3 each time. Okay, something else, we're also extending it in 3 different legs. Okay, but we're not affecting the middle one. So I think that plus 1 would go right there. Now, so the plus 1 is that middle piece. The 3 comes from those 3 legs, and how many are we timesing by? Well, at each step we have 1 less square in each leg. So the 3 comes from the 3 legs, and then the n minus 1, the step minus 1, comes from the fact that on all of our legs we have 1 less. So that's kind of where each piece of it shows up in that pattern. So this pattern is a great one. That would be an excellent one you could use. Very easy. Okay. Now number 12 has a different way of writing them. S equals 3n minus 2. Okay. Does this one work? Well, let's take a look at it. Okay. Once again, the n stands for the steps, the step number, S stands for the tiles. But where can we see the information in this one? Okay, where do we see this 3 and where do we see this minus 2? Kind of the same way. The 3 comes from the fact that we have 3 legs here, right? 3 legs. And according to the step number, each leg has that many. Okay? It's like if I were to write these separately, I have 3 blocks here, I have 3 blocks here, and I have 3 blocks here. Okay, but what we do is we smush them all down together. So we take those 3 pieces and we're really mushing them into 1. Okay, and so 3 minus 1 is 2. So that's where the 2 comes from. The fact that you're overlapping 2 of those squares with the first square. So the 3 comes from the legs again, and that minus 2 this time comes because you're counting all pieces of each leg, but since they overlap, you've got that minus 1. So, could you think of a answer for number 10? Possibly. Okay, there could be another way of doing it. These ones are 2 great ones. The one that I came up with looked very similar to that one. So, hopefully that helps a little bit in that understanding. Now, 2 of the last type of problems just dealt with a line and a slope. If we look at number 13, they wanted us to plot these 2 points. So if we plot them, 2, negative 1 goes right about there-ish, and 4, 2 goes right about here. And then they told us, we draw that line. What is our slope? Remember that slope is rise over run. So it's how we go from this point up and over to this point. Well, from this point we're going to go up 3 and over 2. That's where the fraction 3 over 2 comes from. For number 16, they want us to plot the points. So negative 3, 0 would be right there. 0, 5 would be up here. And then they want us to find the slope. If I were to draw the line, it would look something like that. I'm not very good at drawing straight lines. So how far up do I go? Well, 1, 2, 3, 4, 5. We go up 5 because we went up, it's positive. The rise is how far up or down you go. So my top number is 5. The bottom number is how far to the right you go. So if I count 1, 2, 3, I went over 3, so my slope would be 5/3. So that was the Getting Ready 1.1. Let's take a look at Getting Ready 1.2. Now these problems are a little more difficult, okay, but we can still deal with them the same way. Now if we look at number 4, probably the easiest way you remembered how to do this was to cross multiply, where you took the bottom of one side, times it by the top of the other side, kept it equal to the top of the other side, times the bottom of that other side. 7 times 11 is 77. 7f times 11 is 77f. Then you just divide by 77 on both sides, and you end up with 1 equals f. Okay, something else I want you to pay attention to, which I think is actually easier than doing it that way. Don't worry, yes, I'm erasing it, but all you have to do is back it up, and you can figure it out. So if I'm looking at this, okay, I've got two fractions here. Yes, that's true. They're called proportions when you set them up like this. Notice that my bottom numbers are the same. Okay, whenever you have the same bottom numbers, you can basically get rid of them, and you'd end up with 7f equals 7. Okay, notice they're also the same. So the only way that number that 7 times can equal 7 is if f equals 1. Okay, so pay attention to that. So there's that cross multiplying, or just try to notice the numbers. Now number 5, we've got a fraction, but this time it's only on one side. So we're going to have to deal with it. Now, the easiest way to get rid of a fraction is to do this. Multiply by its denominator. Okay? Since it's an equation, I would do it to both sides. If I multiply by the denominators, the denominator and that number cancel out, leaving me with 2 on the right side. On the left side, I've got to distribute this 3 to 5q minus 7. It's got to multiply both numbers since they're on the same side. So 3 times 5 would give me 15q minus 3 times 7 would give me 21. Then I would just add 21 and solve this like we did the other ones. We get 15q equals 23. Divide by 15, and I get q equals 23 over 15. Or if you changed it to a mixed number, 1 and 8/15, or 1 point some decimal. Okay, I think that's an easier way than trying to add that 7 to the 2/3. You could do that. You could do it that way. But I think that trying to get rid of your fractions to begin with is a lot easier. Now number 6. We've got a parentheses here. According to order of operations, we deal with it first. I can't combine what's inside, so I'm going to have to multiply. Okay. Now notice we've got a minus here. The way you have to think about that whenever you have a minus in front of a parentheses is to pretend that it's a -1. So we're going to take this -1 and we're going to multiply it in there. So I get 5x plus -1 times 3 is -3x plus -1 times 2 is -2 equals 1. Then let's combine what we've got. This 5x and this -3x are on the same side, so just go 5 minus 3. That would give us, 2x plus -2 equals 1. Now it's a -2, so I add 2 to both sides, giving me 2x equals 1 plus 2 is 3. Divide by 2, and I get x equals 3 over 2, or 1 1/2, or 1.5 if you typed it into a calculator. I would keep it this way. I like dealing with those much better than I like dealing with other things. Okay, so a bit more difficult, but still the same kind of concepts. Alright, now we've got another pattern one. This time, however, they want us, and pay very close attention, perimeter. They want us looking at the perimeter. Remember, perimeter is just the length around. So if we look at step 2, don't count that. If we look at step 3, don't count those. So we just count around. 1, 2, 3, 4, 5, 6. So perimeter of 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perimeter of 10 on step 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we've got 14 here. So, how is this growing? Well, it looks like we're adding 4 each time. So, my guess, step 3, step 4, I don't have room to draw it, but if I added on another hexagon here, okay, then that one wouldn't count, but we'd add 1, 2, 3, 4. Okay, so yeah, the pattern's going to keep going. The pattern is going to keep going. So for step 4, we would have 18. So step 5 would give us 22 because we added 4. Step 6 would give us 26. Now, once again, step 25. Do we really want to do that? No, that's going to be way difficult having to count that far. So we want to try to come up with a rule like number 9 says to help us figure that out. So you have to look at the pattern and try to figure out what's going on. Okay? So I'm not going to worry about 8 and 9 right now, but let's take a look at 10 and 11, because some people once again gave us some expressions that they think would help us with that. So look at number 10. Marcia came up with 1 plus 5n minus n minus 1. Okay, so let's see, we had 6, 10, and 14 for our pattern. So we've got 1 plus 5n minus n minus 1. Remember that n equals the step number. So we want to figure out how do they connect. Okay, how do those numbers connect? So, and we're just talking about the perimeter. So notice this 5. Where does that 5 come into play? Well, think about it this way. If I'm adding another hexagon, since they overlap, how many pieces do I actually add? 1, 2, 3, 4, 5. So for every new step, the n, I'm adding 5 to it. Okay, so for each step, we're adding 5. Step 1, we added 5. But we also have to take into account the ones that don't overlap. Okay, that's where the plus 1 comes into play. Because here we had added 5, and we multiplied by 5, and then we added 1 to it. Step 2, we had one hexagon, we added 5 to it. Okay, from the original 5 that we had, and we would add 1. But what's the problem with that? Well, if we add 1 to that, that's going to give us 11. That's not the answer. So that's where the second part comes in, the n minus 1. Notice for step 2, we only have a middle piece that's 1. So I go 2 minus 1, which would give me 1, which eliminates that 11th and gives us 10. So step 3, so those middle overlapping pieces, that's what that piece right there stands for. That's kind of how it's given you that. Okay? And you could use that one to help you figure out number 8. You could go 1 plus 5 times 25 minus 25 minus 1. So that would be 24. 5 times 25 is 5 to 125 plus 1. So 125 minus 24 would give us 101, plus 1 would give us 102. So if you counted by 4s, step 25, you should get to 102. Okay, let's take a look at number 11. Number 11, we have this expression now. Okay, so 6n minus 2 times n minus 1. So where are we going here? Well, think of it this way. For each step, I've got that many hexagons, right? And a hexagon has how many sides? It has 6 sides. Okay, so that's where the 6 times the number of steps comes into play. But remember, when we squish them together, like on step number 3, we have overlapping inside pieces that actually don't count. So this n minus 1, once again, that's coming from the fact that we have 2 middle pieces, or we have 1 middle piece less than the number of step we're on. Then we're timesing this one by 2, because for each squished one, there's actually 2 pieces from those original 6 pieces. So we've got to double the amount that we're subtracting. And that's where those numbers come. Does it work? Well, 6 times 25 minus 2 times 25 minus 1. Let's check it. 6 times 25 is 150. 25 minus 1 is 24. Times 2 is 48, which gets us 102. They both work. A different way of thinking, but that's all right. With these patterns, there's a lot of different ways that we can think about them. Okay, the last two problems. Graphing when we're given a point and a slope, and when we're given an equation. Okay, number 13, we first start by plotting the point. 0, negative 3, right there. Then our slope is 4. Remember, slope is rise over run. So I've got to make this a fraction, so I put a 1 underneath it. Now, I go to this starting point, and then I can build my steps using that rise over run, and then I'll just connect the bottom pieces to make my line. So that's kind of the process we're taking. So I count up 4, 1, 2, 3, 4, to the right 1. That's my next point. 1, 2, 3, 4, to the right 1. That's my next point. So I've got those 3 points. We can connect them somehow, and that was a crappy line, but you get the idea. Now number 16, this gives us an equation. Okay, one way we can solve it is with a t-chart. You choose some x values, lug it into your equation, figure out the y values, and you plot the points. Okay, or we can take this similar idea, okay, because our equation is actually in slope-intercept form. Slope-intercept form gives us the slope and the y-intercept. The y-intercept tells us where it crosses the y-axis. The slope tells us that rise over run. Okay, so if we look at our equation, the 5, the number without x, that's our slope-intercept. So our point is 0, 5, right there. Our y-intercept, our starting point, is 0, 5. Our slope is negative 3. Turn it into a fraction, and then you can go down 3 to the right 1, down 3 to the right 1, or if you're working backwards, up 3 and to the left 1. And then you draw your graph, and you're good to go. Well, I think I've spent way too much time on this, so we're going to call it good and get out of here.